Hello, everyone. Thank you for attending the webinar. My name is John Stancarone, and I'm engineer and product specialist with T Equipment. We've got a really great webinar for you today. Volney Naranjo, Renewables Business Development Manager with Megger, will be here presenting measuring resistance in photovoltaic installations. Volney received his BSEE from Universidad de Valle in Cali, Colombia, and after graduation, he worked in electrical design and testing and commissioning of power systems as a field engineer and product manager. He joined Megger in 2011 as an application engineer, focusing on the products for transformer, low voltage, and high voltage circuit breaker and battery testing. Currently, Volney is the Renewables Business Development Manager for North America at Megger, and he is an IEEE senior member and has published multiple articles and conferences such as TechCon, Power Test, TSDAS, BATCOM, IEEE, EIC, and Offshore Wind Power, as well as various other technical magazines. I want to bring your attention to a sales promotion that Megger has going on right now, which will allow you to save a lot of money on some really great Megger tools. I'll be adding a webinar chat link to the webinar chat. I advise you to take a look at that. Click on that because you'll see some really good savings there. Now, before turning the presentation over to Volney, while we're waiting for any late joiners to join the webinar, I have a couple slides about our company that I wanted to share with you. Now, we have just recently celebrated over 21 years in business, and in that time, we've become a very large stocking. We really do take to heart the slogan, buy from people, not just the internet, and we have a highly qualified staff that is here ready to help you. As you can see from this slide, as a national and international distributor, we cover the needs of a wide variety of customer types on the left side. The right column there shows you some of the products and instrument types we carry. In total, more than 500,000 products. Many different things, and we're getting new things in all the time. As you can see from this next slide, we have invested heavily into our website and made it basically a really great resource to use. You can see we have some filtering criteria there on the left side of the page. There are many more. That one really just shows you the type of this type of equipment, but you can also search by pricing and things like that. So it's become a very useful tool that we use internally as well. So hopefully you'll find that very useful. Now I'd like to turn the presentation over to Volney, and he's going to start the presentation for you. Volney, thank you for coming.
John, thank you so much, and thank you to everybody attending to the webinar. I hope we answer a lot of your questions in relation to measurements of insulation resistance and low resistance in photovoltaic applications. And let me get ready here to share my screen. And screen, no, this one. Okay, you should be seeing my screen now. Let me know if that's correct.
Yes, I see that.
Okay, good. So, again, my name is Volney Naranjo. I'm the Renewables Business Development Manager for North America in Megger, and I help navigate the Megger world to different customers and to understand all our applications and our products. So today, the agenda that I have for today is the first, measuring electrical resistance, like the different measuring ranges, the methods, the test current, the measurement modes as well, and some measurement comparisons to show you that depending on what method you use, you would get different results. Then we are going to talk specifically about bonding, why we need to test it, the standards, expected results, and causes for high readings, and some final recommendations about that. And for insulation resistance, of course, we're going to define it, and we are going to show the recommended test method and result interpretation. Really, the presentation has a heavier focus on bonding, but insulation resistance will give you the basics to ask more questions or come to us and let us know how can we help. So let's get started with the measuring of or measurement of electrical resistance. So here you can see um, uh, a wide range of values to be measured. So starting at 100 nanoohms, which is very, very low, up to 1 teraohm. So totally opposite ends, very, very far from them. And all of these is measuring resistance. So really, you have a very wide range to measure, and not in one single instrument is not going to help you, or it's not going to be able to measure all what you want. So you want to define a method and an instrument to be able to perform the measurement. And as you can see at the top, I'm kind of mentioning 3 methods there. So for the high resistance measurements, I have the 3-wire, and that's basically insulation resistance testing, which typically goes from a range of 10 kiloohms to 35 teraohms. The voltage that you apply can go from 100 volts to 15 kilovolts, and it's dependent on the application. The current is not too high. It's in the order of milliamps, and it can go up to 6 milliamps. Under these conditions of measuring such a low current, you're going to have very likely noise in some of the environment or some of the conditions that you test. So you want to have some noise rejection. So typically instruments can go up to 8 milliamps of noise rejection. Oops. Then another section in this range is the typical digital multimeters. And these digital multimeters can measure resistance, absolutely, or definitely they can measure. However, you can see the range of measurement is very limited. From 1 to 60 mega ohms. It uses very low voltage, 5 volts, and very low current to do this measurement. Next, we have much lower resistance measurements from 10 milliohms to 1 kilo ohm. And this is typically used, or it's the typical continuity tester, which is probably a functionality in many or several digital multimeters. And you could have a little bit of better accuracy or lower measurements there, lower range or lower side of the range, but still it's not going to be that accurate because the voltage and the current that they can use is might be limited. And then you have what is called the low resistance testers, or the digital multimeters, sorry, digital ohmmeters, or digital low resistance ohmmeters. And they can go from anywhere from 15 nano ohms to 2 kilo ohms, with voltages from 1 to 6 volts and current or test currents from 1 milliamp to 10 amps. So this is already telling you that, okay, resistance measurement is something that definitely I need to understand and know what tool I'm going to be using for the application that I have. So moving on to the concept of the measurement, well, from my previous, or the previous slide where I was showing the specs of the typical instruments, I always talked about voltage and current, because that's what we do when we want to measure resistance. We apply a voltage and we measure a leakage current, or we apply a current and we measure a voltage drop, and with those 2 parameters we can calculate the resistance. So basically that's what we're going to be talking about during this presentation. So typically this is showing the setup, or the diagram for a resistance measurement, a low resistance measurement. So you see that there's a current generator, there's a voltmeter, and you have the object under measurement represented by the R there. And as you can see, there's going to be a current circulating, and there's going to be a voltage drop across the resistance. And those two parameters are the ones that you use to calculate. So let's get a little bit more detail, and there's a method that it's called the two-wire method. This is basically what I was showing in the previous slide, but with a little bit more of detail. You still have your current generator, you have your voltage meter, and this shows that there's the leads connecting from the instrument to the resistance under measurement. Those leads have a resistance. Definitely they're not perfect conductors, so they're going to have a resistance. And if you use the two-wire method, basically that voltage drop that you are interested in measuring is being measured at the terminals of the instrument. So in your result, you are going to get not only the resistance that you are interested, but twice the resistance of the lead, or each of the leads. So that's going to be your total resistance, or your resistance measured. So you're not going to get an accurate value. This method is the simplest method to use to measure a resistance. But the longer the leads, the bigger the effect on the measurement, and it's the least accurate method for low resistance measurement. So it is good for continuity, but definitely not the best method for low resistance measurements. The continuity verification, or for industrial applications, it's a very good method, and this is what you typically see in the digital multimeters. You see a symbol of resistance, and you also see the buzzer symbol, because you can get a value of resistance, but just with a beep you can determine that you have continuity or not. However, because of the voltage and the current that is used for this measurement, you're not going to have the most accurate value, and we're going to see an example of that. Then the four-wire method. Well, in this case, this is known also as the Kelvin measurement, and in this case, two wires are used to circulate the current through the object that we want to measure, which is this one. And then two separate cables are used to connect the voltmeter to the object under measurement, or the surface that we want to test. So now the current is going to circulate. You can see the current circulating here. And because voltmeters have a very high impedance, the current that is going to circulate through these wires is very little. So really, you are measuring the voltage at the terminals of the resistance that you want to measure. So that is going to give you a much accurate value. You need four wires, two for the current and two for the voltage measurement, for the voltage drop. And with this, you get precise measurements, and typically you see represented these in the instruments, like with a little rectangle and two conductors, like it is shown here. Now here you see some arrows. We're going to talk about that in a minute. But basically, when you are measuring a resistance with higher accuracy, you're going to see this symbol used in the test instruments. So the next thing to cover is about the current magnitude when we want to measure low resistance. So what is the best, or the current to use for the measurement? Basically, the current that you use, the magnitude of the current, is going to determine, or is going to give you more resolution or lower resolution in the measurement. So meaning that higher current will give you higher resolution, much better result. However, you don't need, you cannot use high current in discriminated way, because then you're going to heat the sample or the surface or the contact that you want to test. And if the temperature in that surface changes, then the resistance that you're going to measure is going to be dependent on temperature, and you don't want to do that. So you want to use a current that can give you a accurate result with high resolution, but without exceeding. So typically the low resistance ohm meters, they have a wide range. Typically, well, not in one single instrument, but typically you see a range between instruments of 100 microamps to over 200 amps, and there are instruments that can do 600 amps. Now, for bonding applications, for continuity measurements, there's no need of such a high current, and at least you should be above the 100 milliamp. Below that, below 100 milliamp, the quality of the connection is not tested. Yes, you get a continuity value, you get a beep indicating that you have a connection, but you are not measuring the real resistance of that connection or the quality of that connection. And if you have noise in the measurement, or you have different temperatures across the metals that you are testing, then you're going to have what it's called thermoelectric voltage, or EMF. And this noise is going to affect your measurement. So you typically want to have a current that is higher than the noise. 100 milliamps is kind of low, so you want to have a higher current for that. So for bonding applications, 200 milliamps is enough for bonding testing. However, the recommended value from our end is 2 amps. 2 amps is more than enough to get a very accurate result in bonding applications. Breaker testing or other applications, definitely you need above 50 amps, or at least 100 amps. So that's depending on the application. Just to give an example of how the current magnitude affects the measurement, this is not exactly like a bonding application, but it's a connection of two terminals in a battery. So basically, we want to measure the resistance of this contact plus the resistance of this contact here for the strap. So basically, one side of the instrument is connected or touches the post, and the other side of the instrument touches the other post, to be able to measure this contact resistance plus the conductor plus this other contact. So we perform the test with different currents, and with each current we perform the test multiple times. So here in this graph, what I'm showing is the variation or the average deviation between measurements. So let's say we perform 10 measurements with 100 milliamps, and we did it also without noise and with noise. So without noise, you can see here that the 100 milliamps between, or the average deviation between measurements, was 21%. So definitely no accuracy there. And you can see that, funny enough, the noise is helping you to get a better measurement, because again, noise is extra current. So in some cases, the noise can help. And as we increase the current, you can see that the error or the deviation changes or reduces. And well, it's a strap application, so it's a battery application, not a bonding application. So you can see that the higher the current, the more accurate or less deviation between the results. And when we injected a current of 200 amps, now the result has also a big deviation between the different tests, because now the temperature of the sample or this connection changed, and now the temperature changed. So you can see here basically all the benefit of testing with the right current and using the right magnitude. Then the measurement modes. The measurement modes, we have the unidirectional. So basically, from the initial drawing that I showed, you see the current here, and that current is basically circulating in one direction. So it's doing this, and you get the result. You can also do current injection in one way, and then reverse the polarity of the injection and inject on the opposite polarity. So in this case, that's what it's called bidirectional, applying current on both forward and reverse direction. And the final result is the average of both measurements. What this does is that this cancels the noise, the thermoelectric voltages, any floating currents, anything that is affecting the result will be eliminated with that. In that way, you only get the actual value of the resistance that you are intending to measure. So depending on your application, you may want to use unidirectional, bidirectional. It adds a couple of seconds to the measurement, so not a big problem to use this method to get more accurate results. So now let's see a couple of comparisons. So this first is comparing the two-wire measurement in two type of connections, one loose connection and one tight connection. And basically, because it's a two-wire method, we're going to be doing continuity test here. So this is the loose connection. This is something I did. I tied these with my hands, so no tools. And running the test, you can see here the test. I'm running that measurement, and it's giving me a result of 100 milliohms. And then this is a connection that I did use tools to tie that connection, and it is giving me a measurement of 90 milliohms. So just a difference of 10 milliohms. Now let's use the two-wire method versus the four-wire method on the tight connection. So we're going to focus on this connection here. So we already know that with the continuity test, we got the 90 milliohms. And then here we have the four-wire method using 1 milliamp, very low current still, but we are getting 4 milliohms of as a result. So you can see here that there's it's an 86 milliohms difference, 183% difference between the two measurements. So if you just want to verify continuity, yes, but what is the quality of that continuity? You're not going to see it with a continuity measurement. You need to use the four-wire method to know if you really have a low resistance. And we're going to see, or we're going to talk about why it is important to be sure that it has a good quality connection there. One more comparison, the 1 milliamp measurement with the four-wire method versus 1 amp. So now basically it's the same connection that I'm going to measure. It's going to be the same instrument with the same method, the four-wire method. The only change is that now we have higher current. And with 1 amp, we have a result of 0.022 milliohms. So from 4, we went to 0.022. That is almost the 4 milliohms difference, 4.978, and almost 200% difference. with the same instrument, but just changing the amount of current. So now I can see the real value or the real um, resistance of the connection. And if I use this result of 90 milliohms to calculate how much heat is going to be dissipated there, it's going to give me a very high result. So, and that's what you don't want when you have a bonding. You don't want to have a high dissipation of power. Now, for bonding purposes, you don't have current constantly flowing through that connection. So let's talk about bonding and see what is the definition and what the standard said. So if we look at the NFPA documents, bonding is a connection to establish electrical continuity and conductivity. It's kind of a very broad definition, and it gives you a very good idea. However, the IEEE definition says that the electrical bonding is the electrical interconnection of conductive parts designed to achieve a low impedance conductive path. So this for me is kind of a key. You want to have a low impedance conductive path, and if you're talking about low impedance, you're not talking about conductivity. You're talking about an actual low resistance. IEC, it's probably not a common standard for us, but especially in the photovoltaic systems, they are ahead of the IEEE standards, and so typically those are used as reference here in the US as well. And for IEC standard, equipotential bonding is the set of electric connections intended to achieve equipotentiality between conductive parts, and equipotentiality is the key word here. We want to have the same everything at the same potential in a connection or in a surface that it's going to be probably exposed to voltages. And because if you achieve that equipotentiality, you have a safe system. So bonding, again, is equipotential surface. You want everything at the same potential. If there's a connection to a voltage source, and you want that equipotential surface because if you don't have it, there's going to be potential difference, and that it's going to cause circulation of current between the surface and ground or whoever touches that. So it can affect, if you don't have an equipotential surface, you're going to affect the personal safety, or it can damage equipment from voltage surges or static electricity. So if for any reason any part that is intended to be grounded has a potential difference, that becomes a safety hazard. The other big purpose of having an equipotential surface is to have a proper path for lightning protection systems. And if we want to give another reason of why to test bonding, you could easily say because the NFPA standard 70B tells you that you have to do that, and it's mandatory for large multifamily residential complexes, industrial plants, institutional buildings, commercial buildings, and also utility scale installations. And of course, this is going to be depending on the authority having jurisdiction, but that's one of the main things that they check. It's basically safety of personnel. If we look at IEC 62446-1, this is the standard or the requirements for testing, documenting, and maintaining photovoltaic systems. And they also mention that this is a test that shall be performed. These are a couple of slides I have showing screenshots of these documents that I'm mentioning. So from NFPA 70B, the fundamental test is one of the contact resistance is one of the fundamental tests. it tells you that you should use a calibrated instrument to obtain contact resistance test values. So this is not telling you to do a continuity test or a verification. You want to get the actual contact resistance values. And once you have those results, you want to compare to the values published by the manufacturer or the specifications from the manufacturer, and anything deviating from that shall be investigated. So it's mandatory. It's an actual fundamental test, and they want you to get actual values. It has a section, NFPA 70B has a section 30.4 for electrical test, which is for testing photovoltaic systems. And again, it shows that you should test your grounding and your bonding. And one of the methods, they talk about several methods, and one of the methods is contact resistance. However, let's talk about the other methods: infrared thermography, fall of potential, point-to-point, current reading, and calibrated torque. So all of these methods are going to give you some idea of the connection, if it is good or not. And especially infrared thermography, it's only going to help if you have current circulating through the connection. If there's no current, infrared is not going to tell you much. And torquing is not necessarily giving you a good connection. If you have some contamination, or if you have some foreign object or something that doesn't go between the connection, you could torque that very good, but it's not going to give you the right result, or it's not going to give you the right resistance for that surface. So I have here the frequency of maintenance. NFPA also shows the frequency of maintenance, and for grounding and bonding, it shows all electrical testing shall be done according to this schedule: 60 months for condition 1, 36 months for condition 2, or 36 months for condition 3. And it also talks about photovoltaic systems. So different parts basically from this standard tell you that in photovoltaic systems you need to do it. IEC, again, it's not that common here in the US, but it also, this standard for photovoltaic systems, it shows that the tests shall be carried out in one of those tests is the bonding of the conductor. So you need to test those according to this standard as well. So if you want, you can receive the slides, and you're going to see all of these details in the slides. So how to perform the test? So here we have a typical depiction of a solar array. You have multiple panels connected in a string, and then you have different racks with more, or several racks with more strings like that. So the first thing to test is the interstring, and of course you don't want to measure each of the bonding connections. That will be a lot of testing and a lot of work. But if you measure from end to end, that is going to give you a very good idea of the conductive path throughout those connections or those panels, the frames or the rack system of the panel. And so basically you want to use or connect one of your leads here and the other set of leads here. So in the end, you're going to have your instrument somewhere in the middle and a set of long leads. So this also tells you that the two-wire method, it's not going to help you, because this resistance of these conductors is going to be much higher than the resistance that you want to measure. So you need to use a set of reels to be able to do this measurement. And here, this video shows you like we have a reel at one end of the rack. We extend the cable, and then at the other end we connect the other lead the second lead, and that right there next to it is that you perform the measurement. So you can see that the instrument already has the other lead connected. Each set of cables has two wires, so you have the 4-wire measurement, and that's why it shows black and red, that clip there. And once both ends are connected, then you can run the test. And the typical measurement that you expect is 5 milliohms or below 5 milliohms, all of these bonding here. In this case, you should have, or the ideal thing is to use a high resolution instrument with high power. Now you have a long path to measure, and you want to have an instrument that can give you the resolution and the current to perform this measurement. Okay, so oops, let's see. Yep, this is kind of another depiction of this measurement. You can see, well, one lead is here, and it has two ends. Let me see if I can zoom this in. Where's my zoom? Oh, I don't have a zoom. Okay, so here you have two prongs basically. One is for the voltage, one is for the current, and you can see that there's a cable coming here, and it's extending to the other end of the rack, and that is connected at the other end. So that's how you perform these measurements in the field. And then you want to perform the measurement between the strings or between the racks, string to string or inter-rack. So basically you can do the test from this end to this end, or you could do it somewhere in the middle from this point to the other end here, and that's what we have here in the pictures. So here you don't need such long conductors, and basically you're connecting a set of leads here, your instrument is in between, and then you have the other set of leads here. And the current circulation, of course, is going to be going all the way down there and coming back here, and the same here. It's going to come all the way and it's going to return. So it's going to be a parallel path for the current. But anyway, that's going to give you the measurement, the calculation of that resistance. Here you can see the measurement. So somebody has the instrument here, one lead is connected here, the other lead is connected here. And that is giving us the measurement in between the racks or in between the strings. Why can you have high readings? So basically, or one of the reasons is having a loose connection, or the other extreme is also bad for low resistance, or for achieving low contact or low resistance contact. If you over tight the connection, that is going to change the physical contact of the two surfaces, and that this is the typical curve of a torque against resistance. So low torque, you have high resistance, then you have the optimal torque, that's where you get your optimal resistance, but then the deformation of the surface is going to increase the resistance. So, and you can see it here. So if this is over torque, you can see how this surface is not anymore flat in 100% contact, but it's reducing the surface of contact, and that is distorting the resistance. Also, you could have some extra hardware. So let's say somebody used a washer here. And this is where I was saying, if you torque this to the spec, yeah, the torque value is going to be good. But what if you have something here in between the two surfaces that you want to make the connection? That is going to increase your resistance there. Corrosion, after some aging of the connection, you could have some corrosion there. And the other reason could be external. You could have noise or induced currents that affect your measurement. So once you get a result, and if it's out of what you're expecting, then you want to check all of these aspects. If you have the right torquing, if you don't have anything in between, or you have contamination, or if you have probably you're using a very low current, that it could be affecting your result. So just to summarize the bonding section, you want to have the proper test instrument. You want to understand the specs, what voltage, what current it is using, in the measurement range, how low can it go in the measurement. You want to pick your test method. Really, for bonding measurement would be the 4-wire. Definitely not continuity verification won't be the best way. 4-wire, it will give you the correct result. Measurement mode, well, it depends. If you typically you can use the unidirectional, but bidirectional will definitely give you the accurate result, and especially because you have such a long distance to measure, you could have different temperatures in between those sections, and that is going to affect your result. So you want to use bidirectional. If you have long distances, you want to use an instrument with a high power output. That means that it's not the same to inject 1 amp with a source of 5 volts, or 1 amp with a source of 10 volts. You have more power there. So you want to use an instrument that has higher power there, meaning not only the current, but also the voltage. And you need to have some long leads if you have this situation of long measurements, long distances. And measurement spots, you want to designate and mark the measurement points for consistency and repeatability. So going back to my previous slides, if I'm doing the test, I would like to mark these here for future reference, and this spot also for future reference. So that way, every time that I make the measurement, I'm doing a repeatable measurement, or I know that I'm going to get the result. That if I get a different result, it's not because I connected to a different spot. And what tests to perform: interstring, string to string, and then you want to troubleshoot high results by testing different sections. So you start dividing and conquering, basically. So this is about the bonding testing, the low resistance measurement. As I mentioned before, the presentation is heavier on the bonding side. But now let's move on to the insulation resistance. What is insulation testing? Basically, it is the measurement or the test that you perform to determine if you have a good quality insulation, and basically a test to determine if your insulation is containing all your electrons there. So, and I use this sentence to kind of as a segue to the analogy that we have here. So we have that electricity in a wire is like water in a pipe. If you have water with low pressure in the pipe, you might have a pipe or a hose with a defect, but because there's no high pressure there, you're not going to have a leak. But if you increase the pressure, well, this is what could happen. And you have a leak, and the more pressure you apply, the more leakage you have. So the same applies in electricity. If the voltage basically equates to the water pressure, to the pressure that you apply. And ideally, you want current to circulate only through the conductor, so through the pipe. But if you have a defect, then that's going to leak somewhere there. And the same happens with the insulation. If you have this insulation deteriorated and it's connected to ground, then that is going to have some leakage there, and that's going to affect your installation. So that's what we are doing with the insulation. We're applying a voltage, and we want to determine if there's a leakage. A little bit more about insulation. So you can have your insulation, I don't know, with a life of you could have an expected life of 40 years, let's say, of an insulation, and that is under the condition that you're always operating under on this voltage, the nominal voltage. So now, as the insulation ages, the insulating capacity reduces. So the typical curve or life curve of an insulation is this. So at the early stages of the insulation, you have a lot of insulation or a lot of insulating capacity. But as the age of the insulation or as the insulation ages, it's going to reach a point where even the voltage, the nominal voltage, is going to break down that insulation, and you're going to have a failure. So you want to test throughout the life, and you want to test not only at the operating voltage. You want to test in a range that it's going to give you that analogy of or finding a pressure leakage, and but it's not going to damage the insulation, because if we apply a voltage that is close to this maximum voltage capability, then we're going to break down the insulation. So that is what the insulation test does. It does a quality test. It's not a withstand test. That will be a hypot. With the insulation resistance, we want to get a resistance value. We don't want to see if the insulation is going to break down. So how much voltage to use for the test? Well, because we are talking about photovoltaic systems, this table only goes up to a certain voltage. And typically, if you have a system below 500 volts, well, you go with a voltage that is below that nominal voltage. So, well, somehow applies. So if you have 120 volts or less as the nominal voltage of the system, you want to test with 250. Somewhere in between 120 to 500, maximum voltage to apply is 500. If you have a system that operates above 500 volts, then you want to use 1 kilovolt. And if you have a system that is above the 1 kilovolt or 1 kilovolt, you want to use 1 kilovolt, and above that 1.5. And the minimum insulation result that you should get is 1 mega ohm for systems higher than 120. Systems below 120, you could have 0.5 mega ohms or 500 kilo ohms. So now, the higher this value or this result, the better. And it depends on how big is the system that you're testing. It depends on how you are connecting. So there are many factors that can affect or influence the result. But in any case, it should never be less than 1 mega ohm. Around 1 mega ohm, you would like to do some troubleshooting and check connections, check the contamination level of the surfaces, just to be sure you don't have like surface leakage. But other than that, that should be a good result. So with the photovoltaic systems, we have the positive and negative side. In, well, there ways to do it both, or you can do it in open circuit or short circuit. So it is best probably to test positive side to ground and negative side to ground by separating them, by dividing them. So, or you don't need to divide them. You can test from one end, but still on open circuit. And some manufacturers recommend doing the test under short circuit. So you short circuit this end here, and then you run the test. This is also connected here, and you run the test in a short circuit connection. It depends on what your what system you are testing. But anyway, no matter what way or how you run the test, the result should be higher than 1 mega ohm. Below that it's considered a fault and should be investigated. So I mentioned the methods, and for the insulation resistance test, there's also a method to perform the test, that the 3-wire method. And here you see that I only have 2 wires, the conductor applying the voltage, and then the wire returning the current back to the instrument. So let's say because of the characteristic of the measurement or the asset that you are testing, you're going to have multiple paths, but you only want to measure the insulation resistance of this section, so this part. So if I apply a voltage here, what happens is that I have this, I'm expecting to measure this current or leakage current. However, this is a voltage divider, a current divider, sorry, and you're going to have more current being measured than what you really are circulating through your insulation. So you're going to get a result that is not accurate. The 3-wire method, what does is that it guards that measurement. So now you have an additional path for this current to circulate, and that current is not measured. The only measured current is this one here, which is the one that you are interested. So it's called, this terminal or this connection is called the guard conductor, and it helps you to deviate that surface leakage that could happen in some conditions or under some situations. Let's say you are testing a set of panels or a conductor, and all of these is wet. Well, when I apply the voltage here, yes, I may have some current flowing to ground through a fault, but I can also have a current flowing through the surface, and really this current on the surface is not the one that I'm interested. So guard conductor helps you to run the test, and this is a quick example before ending the presentation. Let's say that I have this resistance that is 100 mega ohms, and I apply the insulation resistance test, and I get that result. If, for let's say, I spray water here in all of these surface, and now I have an additional path for current to flow through the surface. So now I have the current due to the resistance plus the current due to the surface. And now I know that my resistance is good, but now I'm getting a result of 77.5 kilo ohms. So that is not a good result. But if I use the guard terminal, the guard conductor, this current here gets deviated, and now I'm only measuring the current that I'm interested, which is the current circulating through the insulation. Those surface currents definitely can create problems, and you want to at least be sure that you are not influencing your measurement because of a surface current. This quick video shows an example of that, how current circulating due through contamination or bad connection. Actually, you can see moisture here. That can create a path, and that can give you a bad result. So, well, I think I'm running out of time, but this is showing an example, different strings, and you have not only the result, a low result. You should not always look on to the actual resistance value. You should look at the voltage. So if the voltage you intended to run the test is not achieved during the test, it also tells you that it's a result that is not valid. So in some situations, I've seen that this value here is, I don't know, 2 mega ohms here, but the voltage is 600 volts when I intended to apply, or when I applied 1500 volts. So the 2 mega ohms is a passing result, but the voltage didn't build up, and that is an indication that there's a problem in the insulation. So not only the result, but also not only the resistance value, but also the voltage at the end of the test is very important. And lastly, you want to trend the value, so it's not a matter of running the test and not taking note of it. You want to test and come back and after some time and retest, and you want to detect degradation. The way to detect that degradation is by trending the values. And you see that this one has 100 mega ohm value, very steady. This one has a much higher value, but at some point it starts decreasing. It's still better than the 100 mega ohms. But if you ask me, this insulation that has high value but has been decreasing, it's an insulation that has problems. So that is something to also take into account when reviewing insulation resistance results. So with that, I am finishing the presentation. I want to talk about this instrument, the IMT 100, which is a Megger industrial multi-tester. And this instrument, in addition to other tests, mainly it can do the insulation resistance test and the low resistance measurement, and of course it can do continuity test. The 4-wire measurement method it can do with 200 milliamps, and you have multiple accessories to be able to connect to the MC4 terminals to be able to measure the insulation resistance, or you have the reels to do the 4-wire measurement for a bonding verification. With that, I've completed the presentation and ready for questions if there are any questions.
Great, thank you very much, Volney. I've got a couple questions here for you. Now, if you do have any other questions that come up to our audience, definitely let us know and submit them via the chat feature, and Volney will be answering them. I do have a few questions here from our attendees, Volney.
Okay.
The first question is, the 4-wire method seems to be very accurate. What can affect or influence the measurement?
Okay, I think I talked about a couple of things. The noise, if you have overhead noise, or if you have the different temperature across the surfaces of the metals, that can affect the result. But there's one thing that I didn't mention, and it's the leads. You have 4 wires, and there are multiple ways to have those 4 wires ready or set up for the measurement. And in some situations we provide, or for some leads we provide like something that is fixed, that basically you have 2 prongs there, and the distance between doesn't change. Or in some situations you could have 4 wires totally separated. In that case, you want to have the potential measurement inside the circuit that you are applying the current. You don't want to have the potential measurement outside conductors applying the current. That is something that can happen. But for the type of measurement, the bonding measurement, typically you use that with the probes that have the prongs already in a fixed position, and you can do the test easily with that.
Great, thank you. Second question we have is, are there any bonding pass-fail values from standards?
So standards, unfortunately, do not. We are not there with the standards. However, from the slides, I think I mentioned one, but I forgot to mention the other one. So within the string, like interstring measurement, you want to have less than 5 milliohms. And from string to string or from rack to rack, you want to be below 100 milliohms. So those values are values that we have seen from the field and from multiple support calls that we get, and those are the typical values. Now, the best thing that you can do, especially in a solar installation, that you have multiple repeated strings and you have the same setup multiple times, what you can do is that you can measure all of them and compare the values and determine what is going to be your characteristic value for that installation if you're doing the things as per the recommendations from the manufacturer. So that can establish your limits, and you can work with those.
Great, thank you. Third question we have is, can a low resistance meter be used to test the integrity of the ground grid and the grounding system?
So grounding grid, grounding system, that is kind of a different application. There are instruments that are specific for that type of measurement, especially for the ground resistance, the resistance of the connection to ground. We have multiple instruments that can do that. But when a ground grid is being built, you know, it's a grid of, or a mesh of cables, and those cables are interconnected in multiple places. All of those connections can be checked before you cover the grid with soil. They can be checked at the spot with the low resistance measurement. So like if it's a CAD weld measurement, a CAD weld connection, once it is done, you can go and check the connection there and verify that it is low resistance.
I see. Now, can another question was, can insulation resistance test be used to find a ground fault?
So I guess that's the purpose of doing an insulation resistance, to determine if you have a grounded system where where it should not be. So with the insulation test, you determine that there's a ground fault. However, and yes, you can go and do troubleshooting. You can divide and test one section of the system and find that it is good. Then you test the other section, you find the problem there in that section. So you keep dividing it until you find the specific spot. However, doing that with insulation resistance test is not very practical. It's going to be time consuming. You need to do a lot of disconnections. So there are other methods to find ground faults in photovoltaic systems, and you can use the voltage method, or you can use a signature signal like a tone or current, and trace that current to be able to find that fault without disconnecting and without intervening too much the system.
Got it. Thank you. One more question. How often should insulation resistance be performed in a photovoltaic system?
Oh, as I mentioned at the end, the measuring the test period, or doing the test periodically, will help you to gather information to determine if the system is degrading or not, the insulation of the system is degrading. I mentioned a couple of standards, and one of those standards was showing the schedule for the maintenance. Condition 1, which is basically that everything is good, was showing 60 months, which is a lot of time. So you don't have to do that often. However, if you are seeing issues or developing very often in the system in a couple of strings, then you may want to reduce that frequency and do the test more often.
Right. Got it. Thank you very much. Looks like we don't have any further questions at this time, so we're going to end the webinar. But if anyone does have any questions that come up after the webinar is concluded, or if there's anything else we can help you with, please don't hesitate to reach out to us via the contact information slide. I want to thank everyone for attending the webinar and for providing this valuable information. And everybody have a great day.
Thank you so much to T Equipment for the opportunity, and thank you to all the attendees.
You're very welcome. Take care, everybody. We look forward to hearing from you.
Bye, thanks.